model is what I've modeled become a meta architecture. So this you can see on my file on right is a photobioreactor. This is part of my work to design a photobioreactor, and this photobioreactor is what I'm calling my meta architecture in this work. Now, I want to summarize the capabilities of this integrated algae culture system. Now, it can biomineralization. That's my bioreactor can agitate and mix all the carbonates and calcium phosphate. Nitrification, it can use the ammonia that is coming from waste waters. It can be from urine, urea to fertilizers from farm and stuff. So it can utilize the ammonia from there, and bioprocessing, bioremediation, oil extraction, and biomass, which is the recycling. Oh, so and I'm not going to be looking at the harvesting product, but I'm looking at the growth of algae. So before this project will start, I have to look at the design scalability, and I adapted the conventional system development lifecycle model from where I start from the project initiation to feasibility studies, and most importantly to the system implementation, program coding, code implementation, review, and the maintenance, which is the evaluation and optimization of the system. Now, what methodology am I going to use? So the adaptive methodology, as I've said, is the system of system approach, where I'm using the Fila SOS wave model. That is, that's where you have the genetic algorithm with your fuzzy inference system. And in this Fila SOS system, we can either use Python, MATLAB, or the fuzzy. So, but the MATLAB has been proven to be the most effective, which is what I'll be using in this work. Now, for the system of system explorer, some of the key functions of this is for data visualization, integration management, and decision support. So I dived into this project last spring, and I was looking for an approach to really know what I want to do about my system, because a lot have been going on for ROG systems like the bioreactor. So I want to know. So let's quickly go. Now, incorporating my genetic algorithm with FIS and using MATLAB, this is my flowchart, my process flowchart, where I have the definition, the meta architecture, the stopping criteria, and for my optimal architecture to my best solution for my genetic algorithm. Now, for my algae systems, I have 27 systems and 5 characteristics that I'm looking at, where I also have 6 capabilities. Now, these values you are seeing are based on cost value and time monitoring values. So because one of my main focus is for cost-effective pollution remediation. And that's why cost has been the main factor I'm looking at. So on my left side, you can see that I have the interface development cost. I have the monitoring development time, harvesting cost, maintenance cost, and the growth rate. All these are put in factors of 0 to 10, 0 to 1. So from the initial values that was gotten from our survey. Now, for the participating systems and capability of the system, the true or false shows that the system is participating when it's true, and the other system is not participating when it's not true. We'll see that on the result. Now, for me to have a system for my key performance attributes, I need a set of equations that would define my CRISP value of key performance attributes for my fuzzy assessor. So I developed these equations for my key performance attributes. So if you look at this equation, quickly take a look at it. For affordability, I'm looking at the cost interface development cost. the cultivating interface development cost and maintenance cost. And for my availability, I'm looking at the cultivating interface development cost minus the harvesting cost. So for my characterizability, I want to look at just the growth rate. What is happening? Is the algae growing? Is the factors that I consider are they really helping the system? Now I'm looking at the robustness of the system, what time is put into the system, that's the monitoring development time. Then for my sustainability, I want to look at maintenance. And in looking at maintenance, I'm looking at reliability and I'm looking at sustainability. This is what this equation is all about. Now I have to define some set of membership functions for my universe of discourse. So I developed between 0 to 100, and I'm using the Gaussian membership function, which has proven to be the best in terms of having a good meta architecture. I wouldn't dwell much on this. So I set 25 rules for my system in order to have a good decision making tools. So I moved from having a very unacceptable system, which is 7, 35, and 16, to a perfect system, which is 6, 2, and 6.2 and 89. And these are my 25 rules. And these rules are able to help the system to define a scripting and also to be able to give an overall solution to the system. Now, this is my trade-offs between affordability and characterizability, affordability, availability. So the set of rules I've said is what gives the crispness of the system, and it what shows how fine or how refined the system is, so that you can be able to adapt, or you can be able to tell to a customer that this is what these rules can do for you when you set them for your system to be able to have an optimized solution. Now, these are my results. Now, for the 27 systems I'm having with my characteristics put together, interfacing and diffusing inference system used with MATLAB. So this is what I got. So if you look at this system, so if you look at this computer, the microscope, the plexiglass, this is my system. This is the bioreactor design. So this is my meta architecture right now. So these systems that are not shaded show that they are not participating at the point where the optimal solution is achieved for this system. That is to say, something like the microscope is only used when I want to check for the algae growth. So it's not part of the system that makes the algae to grow. So that's why it's not interfacing right now, and it's not showing that it's participating in the system. So overall, what have I achieved? I've been able to know that affordability at this point is 71% based on my set of rules and my equations. So, and my availability is 100%. Why? Why is it 100%? Because I have to have all the systems available before my system can work. If I don't have the necessary tools available, I cannot have a good system. I cannot even start the initial phase of my system. Now, for the characterizability, I have 80.74%, which is a good solution. And for my robustness and sustainability, it's kind of fair, but my result shows that I have to look more into the robustness of my system, the rules I set, and the factors that influence the robustness and sustainability of the system. Now, this non-optimal view, it's not relevant, but I thought it would be relevant because while I first ran my system, this is what I got. And so it doesn't make sense to have a system that everything interfaces telling you that all systems are working together. No. So when I set my roles properly, define my genetic algorithm and my fusing inference system, I was able to get an optimal solution for the system. Now, in conclusion, to reduce cost, the amount of time needed to grow the algae from cultivation to harvesting stage was analyzed and optimized. The study focused on system engineering components and recognized the design and evaluating algae system as a meta architecture. It's quite expensive to do, and it's importantly, it exposes way that we can improve reliability, durability, and also minimize cost. So if you look from this system, you can see that the robustness, we need to pay attention to it, and we need to pay attention to sustainability of the system. Now, also, the study offered a useful illustration for analyzing an algae system. It's common but complex architecture using computer intelligence techniques. Now, I will explain something. You may be wondering that, what am I saying? So currently what I'm working on my bioreactor is to put these systems that can monitor all these things I've discussed here, so that when I'm talking about this and I play and I show you my bioreactor, you'll be able to see how all these things are evolving and unfolding. So that's the more reason I'm talking about this now. Now, the future concern I'm having for this system is I want to be able to separate this system into open and closed points to compare systems capability and effectively. Because in this work, we were able to use open points and closed systems for comparison, which doesn't really bring the fineness of the system as you may have it. So in the future, we want to consider open points separately and closed systems separately, so that we can see the real difference between two. Also, we want to be able to improve growth capacities and factors, capture data, so that we can standardize the adoption. Can another engineer working on algae reactors, can they use my data? Can they use my figures? So these are the questions I want to be able to answer in future. And also the value for cost use can also be reviewed by my team as well. So thank you for listening, and I hope you have some questions.